All right, welcome back. We're at 11.1, day 1, sequences and summation notation. Okay, we're going to determine the terms of a sequence based on either an nth term formula or a recursive definition, and use factorial notation. It's going to be kind of a big lesson, so brace for impact. Here we go. Okay, now a sequence is simply a list of terms and or numbers. Okay, that's all it is. So example right there, the following list is in fact a sequence. 6, 12, negative 13, pi, 2/3, 500, and we could keep going if we wanted to. Now notation for the lists or sequences that we'll be using in this chapter will be, okay, we're going to go a sub 1 equals 6. Okay, now a sub 1 is going to represent the first term, a sub 2 equals 12, and etc. You can see all those without me reading them to you. But on the right hand side here, okay, notice that a represents one of the terms or the numbers in our list, and the subscript is the position in the list. So again, a sub 1 is the first, a sub 2 is the second, etc. So another way to say find the 15th term in the sequence is simply to say find a sub 15. Okay, so again, it's a little more efficient way of getting the point across using a little bit of notation. So that's what we're going to use. All right, here we go. Okay, now although the last sequence had no pattern to it whatsoever, we will concern ourselves exclusively with sequences that have a definite mathematical pattern for the purposes of our lesson. So let's go with that. Okay, so a very simple basic one is 2, 4, 6, 8, 10, and etc. Of course, we can keep going with that. Okay, now we can write a formula that determines any particular term in the above sequence because it follows a very definite pattern. So in this case, the formula is a sub n equals, well, 2 is the first term, 4 is the second, 6 is the third. So notice we're simply taking 2 times the position number we are, so 2n in our case here. Okay, so notice we will create our formulas by assuming that we start with n equals 1 and then count up normally from there, so 1, 2, 3, 4, 5, etc. Unless instructed otherwise, and we won't be instructed otherwise in this lesson, so don't worry about that. So always assume n is going to start with 1 for the purpose of what we're doing, and then go to 2 to 3 to 4 to 5, etc. All right, now of course we're going to do other things to that n value, but again, we're going to have n equals 1, 2, 3, 4, 5, etc. Alrighty, write in terms based on the nth term formula. Okay, so the book is going to ask you to give the first 4 terms of each sequence whose nth term formula, or the book is going to call it a general term, according to our book. I've seen nth term formula almost everywhere else besides our book, so I'm going to use nth term formula more so than general term as we go. Okay, so anyway, our first example has a sub n equals 6n minus 5. Okay, so basically, again, what that means is a sub 1 equals 6 times 1 minus 5. And, of course, 6 times 1 is 6, minus 5 gives us a 1. Okay, this is something we're going to be able to work out pretty quickly. A sub 2 equals 6 times 2 minus 5. Okay, 6 times 2 is going to be 12, minus 5 gets us a 7. All right, again, a sub 3, 6 times 3, which is 18, minus 5 lands us at 13. And then the fourth one, a sub 4, 6 times 4 is 24, minus 5 lands us at 19. Okay, so our final list is 1, 7, 13, 19. Now I admit if this was a quiz and you just simply put a big circle around the 1, 7, 13, 19, I would be okay with that as your final answer. But it's a little bit nicer to do what I did in red as opposed to the thing I circled in green. But you make the call. I'll take it either way. All right, just another example of something that's a little bit messier, and you can tell by the appearance. I get that negative 1 to the n plus 1 power over n plus 4. All right, so don't let it throw you. Just kind of plug things in and work it out. Got negative 1 to the 1 plus 1 power, and that's going to be sitting on top of 1 plus 4. Okay, now the negative 1 to the 1 plus 1 power, well, 1 plus 1 is, of course, 2, and negative 1 squared is going to be a positive 1. And on the bottom, 1 plus 4, obviously, is 5. A sub 2. Okay, now negative 1 to the 2 plus 1 power. All right, putting on top of 2 plus 6. I'm sorry, 2 plus 4, which is eventually going to be 6. But anyway, there it is. Okay, so like I said, 6 on the bottom. And then I've got negative 1 really to the third power, and an odd number of negatives gives me a negative answer. So it's really negative 1 sixth. All right, a sub 3, negative 1 to the 3 plus 1 power, all over 3 plus 4. All right, so I get a 7 on the bottom. That's the easy one. Let's do that first. Then I get a negative 1 to the fourth, and that's a negative to an even power. And if I take negative 1 to an even power, I'm going to get positive 1. So basically, notice what's happening there is we have a way of making our sign alternating back and forth. Okay, so that's what that fancy negative 1 to a power thing is if you ever need to generate some sort of a list that goes from positive to negative back and forth, basically you include a negative 1 to the n plus 1 power or some other exponent that gets the job done that you're trying to do, and that's how you can accomplish your goal. Okay, so anyway, after all that stuff that I just said, I've got negative 1 to the 5th power, which will give me a negative 1 ultimately, and then 4 plus 4 on the bottom gives me an 8. All right, so a little bit messier pattern, but negative 1/5, then negative 1/6, positive 1/7, and then negative 1/8. And again, I'm sure you could generate a few more now that you see what the pattern evolving is. And there you go. So again, basically just plug it into the formula, work things out, and you will see certain things in those formulas, and those things are generally meant there to do a specific job. But anyway, there it is. Okay, again, just like the last one though, if this was a quiz and you just put a big circle around all those guys, I would be okay with that, but it's a little bit nicer, of course, to do what I did in red with the box as opposed to the green oval thing. All right, moving on. Okay, another sequence is defined recursively. This is a bit of odd notation to get used to, so here it is. But in some situations, such as computer programming or coding, okay, it is convenient to have a starting value and then determine the next term or terms based on the previous one, or your starting one. All right, so here we go. Starting with 5, we're going to create a list where each term is 3 more than the previous term. Okay, now without being overly fancy here, I've got 5 I'm starting with, and I want to go 3 more than the previous term, so, well, 3 more than 5 is going to be 8, and then 3 more than 8 is going to be 11, and then 3 more than 11 is going to be 14, and then notice we can go ahead and do this for quite some time until we get really, really bored. But anyway, there's your basic sequence there. Okay, now let's look at how to represent that situation in another way, because again, mathematicians, we like to come up with efficient ways of doing things. Sometimes those efficient ways, though, are a little harder to understand, but here we go. So, starting with 5 just means that a sub 1 equals 5. Okay, and you can kind of see that down in my little description down below. Okay, and then each term is 3 more than the previous term, just means we add 3 each time, and that's actually what this fancy notation right there does. All right, so anyway, here we go. We can represent this mathematically using the recursion formula or recursive definition. Both terms will get thrown around from time to time depending on what textbook you're looking in or who you're talking to. But there it is below. Okay, so like I kind of mentioned, okay, we're going to have our first term, which is going to be a sub 1 equals whatever we're starting with. So in this case, a sub 1 equals 5. Okay, and then the critical one, I think, the more critical one, but again, that's my opinion, any term after the first term is what a sub n is going to stand for. Okay, and then you're going to see equals, and then there'll be some kind of expression, and it should include an a sub n minus 1. Okay, that's just a simple way to say the previous term, that n minus 1 thing. And then there'll be something that's happening to that a sub n minus 1. In this case, it's just simply a plus 3. Okay, now you'll see beyond that, we've got this for n greater than or equal to 2. Okay, now this is typically not given in most textbook like that says there, but our textbook likes to do it. But it's kind of redundant with the any term after the first term sort of thing. Okay, so the a sub n in the middle there, okay, we want that n to be at least 2. So we're not going to say a sub 1 equals 5 and then allow you to say a sub 1 equals something else. But anyway, it's a little tough to get through all the junk I've said there. So let's go to the example here. So let's do another one, make sure we've got it. And here's all that mess in action. Hopefully it'll make more sense when you see it kind of taking place. All right. So again, the directions of the book are going to be write the first 4 terms, and here we are. Okay, now the good news is, well, a sub 1 equals 4. Well, that's the first term. So as far as my final answer goes, it's 4 comma, what else is going to happen is yet to happen, but let's figure it out. Okay, and then to get a sub 2. Okay, so here it is. If I want a sub n to be a sub 2, that means I want to take 2 times the previous term. So remember, the a sub n minus 1 is the previous. Okay, in our case right here, previous is the first term. So that 4 just comes down there. All right, and then we've also got the minus 3 as part of our formula, and then there's just something to work out. 2 times 4 is 8, minus 3 gets us a 5. All right, so in terms of our final answer, it's 4, then 5. All right, now to get to our third term, okay, we want to take the previous term, which is 5, but we're going to take 2 times that. So again, take that previous term. Okay, and then we're going to subtract 3. And at this point, we get 2 times 5, which is 10, minus 3, which lands us at a 7. All right, so the third of our 4 terms is 7, and let's keep going. A sub 4 equals 2 times, again, that previous term, in this case, is now a 7. Then we're going to subtract 3, but 2 times 7 is 14. 14 minus 3 gets us an 11. So there's that. Of course, we could just continue doing what we were doing there if we needed to generate a longer list for any reason, but at least the book's directions said give us 4. So that's how you generate 4 terms if that was the problem you were working on. All right. Hopefully that makes a little sense now that you've seen it in action from the beginning to the end. But of course, as always, if not, ask me in class, and we'll do a couple more examples to help you out. All right, that takes us to factorials. Okay, in many counting and probability problems, we end up multiplying many consecutive whole numbers together. All right, so for example, in a race between 8 people, how many different ways can first through 8th place be awarded? Okay, now this, if you haven't done this kind of stuff before, is actually a very deceptive sort of thing. You wouldn't think this is going to be a very, very large number, but here's basically how it plays out. Okay, so I'm not making fraction bars, although it kind of looks like it. So first is the first blank is for first place, second blank is for second place, third blank is for third place, etc. So then there's 4th, 5th, 6th, 7th, 8th place. Okay, I'm not going to write all those out because I think you get the idea. All right, so for first place, once everybody starts running in the race, okay, well, there's 8 people that have a shot at being in first place. So basically my first place, I've got 8 possibilities. However, once one of those people cross the finish line, sorry there, okay, then that means there's 7 people left to be second place. All right, now 2 people have crossed the finish line. That leaves 6 people working to try to make it to be third place. Okay, and we basically can follow that pattern, times 5, times 4, times 3, times 2, times finally there's only 1 person left to come in 8th place. All right, so to calculate that, we multiply 8 times 7 times 6, etc. And if we do that multiplication, it works out to be 40,320 different ways 8 people can finish in a race. And that's assuming no ties. If you allowed for ties, that'd actually be a larger number. So yeah, again, doesn't seem like 8 people, how many ways could 8 people do something? Well, apparently it's a fairly large number. All right, let's keep going. Okay, now since writing that 8 times 7, etc. is a bit cumbersome, and worse if the starting number is larger. Imagine doing like the Chicago Marathon when you've got thousands of runners, what that would work out to be. Mathematicians came up with a notation for this, and it's called factorial notation. Okay, so 8 times 7 times 6, etc. can be written as 8 with an exclamation point after it. Okay, now that's not us being really excited about the number 8, but it is read as 8 factorial. So we are adopting an exclamation point to do a mathematical thing. All right, so on a basic level, n factorial, or some number factorial, is the number of ways you can put n items in order, like racers in the example problem I did earlier. Okay, now based on that, even though it may seem counterintuitive, what is the value of 0 factorial? Okay, now I'm going to write something and you may not believe me, but if you don't believe me, please type into your calculator and test me on this. But 0 factorial actually equals 1. All right, now again, the gut reaction is probably to say that should equal 0, but you can put 0 things together in, you can put 0 things in order one way. Okay, I want everybody to do this right now. Take 0 things and put them in order, ready, set, go! Okay, so you just did it one way by sitting there doing nothing. So the one way you can put 0 things in order is by sitting there and doing nothing. And that's kind of a joking sort of way, of course, but also we've, mathematicians that is, have defined 0 factorial to be 1 because there are formulas that involve factorials where if you have 0 factorial equals 0, it causes the formula to get some undefined stuff. But if we have 0 factorial equal to 1, the formulas all work out very, very nicely. So in a practical way, that's defined so that it makes sense in some formulas that we have. All right, but anyway, here we go. All right, so let's give the first 4 terms of the sequence. So basically we can mix factorials into our sequence stuff. So a sub n equals n plus 1 over n factorial. Okay, so again, a sub 1 equals, all right, 1 plus 1 over 1 factorial. Okay, a lot of little vertical bars on that one, but here we are. So that's 2 on top, and 1 factorial, well, is 1 times nothing else, but it's just a 1. So there we are. And of course, that reduces down to a 2, so I'll start writing my final answer down below here with that as a 2. All right, a sub 2, so again, 2 plus 1 over 2 factorial. All right, so that's a 3. 2 factorial means 2 times 1. Well, that's still 2, so that's not overly exciting. And 3 halves doesn't reduce. Of course, you could write that as 1.5 or something if you wanted to, but I'm not going to bother doing that. A sub 3, 3 plus 1 over 3 factorial. Okay, now 3 plus 1 is 4. And 3 factorial is 3 times 2 times 1, or again, use that button on your calculator. Sorry I didn't mention it earlier, but it's probably under the probability menu, pun intended. And if you can't find that on your particular calculator, let me know. I'll try to figure out where it is for you if you're not able to find it. All right, anyway, but that's 4 over 6, and of course that's reducible down to 2/3. All right. Now, admittedly, in some of these cases where you have sequences and stuff like that, sometimes answers won't be reduced, or at least if the original question gives you a sequence, sometimes that original question won't be reduced, honestly, to let you see the pattern a little bit easier, because I'm sure you can imagine if there's a bunch of fractions and there's a nice pattern, but some of those fractions get reduced, you might not be able to see the pattern as well. All right, so anyway, just a little side note there. Finally, a sub 4 equals 4 plus 1, rather, over 4 factorial. All right, so 4 plus 1 is 5. Now 4 factorial, 4 times 3 times 2 times 1. Okay, things get bigger quicker here. That ends up being 24. Okay, so things didn't get too big, but they're getting there. All right, now 5 over 24 doesn't reduce, so in terms of our final answer for this problem, there you go. Okay, now again, if this was a quiz and you kind of drew some goofy, wavy thing around there in the green, bubble-ish, snaky form that I just did, okay, that would be acceptable, but again, it's a heck of a lot nicer to write what I did there in red. Alrighty, getting close to being done, but here we go. Okay, now simplifying expressions involving factorials. Now, in certain situations, you can actually work these things out without a calculator. That's kind of the case I'm going to take here, to a degree at least, but here we go. All right, 9 factorial, of course, means 9 times 8 times 7 times 6, and I'm going to do this one kind of the long way just to prove a point. So that's what that means, but then 7 factorial means 7 times 6 times 5 times 4, etc. All right, now hopefully very quickly you're going, hey, wait a minute, there's a whole lot of stuff on top that cancels with a whole lot of stuff on the bottom. You're right, technically the ones cancel, although, you know, what's the point? But the 2s, the 3s, the 4s, the 5s, the 6s, and the 17 all cancel. All right, so really that would just leave us with a 9 and an 8, technically over 1, but again, I'm not going to bother writing that one, so that's 72. All right, however, let's go with a different color here. Or, okay, what we could have done is gone 9 times 8 times, and then keeping in mind what you have in the other half of the problem, you can say, hey, if I go from 7, 6, 5, 4, 3, 2, 1, that's the same thing as 7 factorial. So basically, what you can do is expand the larger of the two terms until you reach the smaller one, and then just cancel the smaller one and call it a day. So notice it leaves you in the same spot, 9 times 8, cool, 72, done. So it's something you can definitely do without a calculator, and you can do it in a fairly compact way if you're paying attention to what's going on. All right, let's take the nastier situation on the right there with a 75. Okay, now I'm definitely not going to write 75 all the way down to 1. Okay, what I can do though is say, hey, I've got a 75 on top, and that's clearly the biggest number in the whole problem, and I've got that 72 on the bottom, which is fairly close. All right, so what I'm going to do is take my 75, break it into 74, 73, and instead of going 72 all the way down to 1, I'm just going to leave it as 72 factorial. All right, now of course that 72 factorial is down on the bottom there. And then the 3, well, I'm going to write that as 3 times 2 times 1, because quite honestly I am going to do some canceling, so let's see what's going on there. Okay, but again, most importantly, the 72 factorials go away. Okay, now here, admittedly, if you didn't have any sort of calculator handy, you could go ahead and multiply the 75, 74, and 73, and then multiply the get that, and multiply the 3 and the 2 on the bottom, get a 6, and take that big number on top divided by 6. Okay, or if you're really, really slick, you can go, hey, wait a minute, 3 goes into 75 and leaves us with a 25, and then 2 goes into 74, okay, and it's maybe not quite so obvious, but that's 37, and then here it's not the funnest thing you'd probably ever have to do, but you could multiply 25 times 37 by 73 by hand. Okay, now I'm not going to make you do that here, or make you watch me do that here in the video, but if you take all that mess and work through it, it works out to be 67,525. So again, kind of maybe a deceptively large answer based on what we started with, but maybe not, I don't know. Whatever your opinion is, that's fine. Okay, but that's how that thing works out. Okay, but again, in theory, you could do it without a calculator, but admittedly with those numbers, yeah, it's probably a good idea to have one. All right, now as it says here, when variables are involved, simplifying factorials gets a little more interesting. Okay, now, if I consider what n factorial means, it means I'm going to multiply the starting number, which is n, times whatever is 1 less than that, so that's n times 1, times 1 less than that, n minus 2, and then I can basically just keep going on with that for a while, so pardon my ellipsis right there after a time sign, it's a lot of dots, but, okay, there it is. And then, of course, starting with whatever the heck n was, I'm going to assume it was kind of big at the start, we eventually multiply down through 4 times 3 times 2 times 1. Okay, but importantly, notice it's n times 1 smaller than n times 2 smaller than n, etc. Now, if I've got variables top and bottom like my example here, where I've got n plus 1 factorial over n factorial, kind of like what I did with the numbers, I want to identify, hey, who's bigger, n or n plus 1? Okay, now clearly, whoops, the n plus 1 is bigger. Okay, so I want to expand the bigger guy until I run into the smaller guy, because then the smaller guy and what's left of the bigger guy can cancel, and you just kind of be left with what the bigger guy had extra. Okay, maybe that made sense, maybe it didn't, but anyway, here we go. So now clearly n plus 1 is bigger, like I said, so I'm going to start with my n plus 1, but I'm going to multiply that by whatever is 1 less than n plus 1, which is just n, and I would then go to n minus 1, except I see that I've got n factorial on the bottom. So n plus 1 factorial would be n plus 1 times n, and again, I can just stop there and call that factorial instead of going all the way out forever. All right, and then that leaves me with just the n factorial on the bottom, which of course makes those two guys cancel, leaving us just with a nice clean n plus 1 as a final answer. So a little bit scary looking from the start, pretty ordinary once you get done. All right, let's try one more that's a little bit messier. All right, so now I've got an n minus 2 factorial on top and an n factorial on the bottom. Okay, now notice who's bigger between n and n minus 2 is the n, because it hasn't had anything subtracted from it like the other guy was. So basically n factorial is bigger. Okay, all right, so again, the bigger guy is the one I want to expand. So I've got the n minus 2 factorial on top, and on the bottom, well, I've got n, and then on times the next smaller number down, which would be n minus 1, okay, times the next thing smaller down, which would be n minus 2, and that's what I have on top, so that kind of lets me stop right there and just end with the factorial. And at that point, I can then cancel the n minus 2 factorials. Now again, very, very important. Notice that there's a 1 technically when you're canceling things in a divide sort of way. All right, so we do have a fraction that will remain a fraction, unlike the last problem, it wasn't a fraction when we were done with it. All right, so I do have a 1 on top, and on the bottom I have n times n minus 1, and that's simple enough to distribute, so I'm going to call that n squared minus n. Okay, now admittedly in a case like that, depending on how messy one of those is, I may or may not have you simplify it, but again, I would include that in the directions if this was a quiz or a review or something like that that I was giving you. All right, and I believe that was the last example. Yep. All right, so hopefully that wasn't too painful. A lot of different ideas here in this lesson, I know, but of course, as always, if there's anything that's kind of throwing you, make sure you ask me in class, and I'll happily explain anything that's kind of troubling you. And I will see you there.